Hi, this is the course General Chemistry 1A, and this is a tutorial for the chapter Properties of Gases. Let's see the question E. There's a carbon dioxide, CO2, which is an isostructural pair molecule of the nitrogen oxide. And then if the mixture of carbon dioxide and the nitrogen oxide gases is cooled down gradually, which gas will condense first? So condensation means that we are going to change the phase of the gas into liquid. So for example, here I have CO2 and N2O. CO2 from gas and then change it into liquid. CO2 liquid, and then the other one N2O from gas and also change it to liquid. So the factor that will affect the condensation is that if we have molecules having stronger intermolecular interactions, then this molecule or this gas will tend to condense faster because of the strong intermolecular interactions. So in that case, we can check from the structure of, for example, CO2 and then the structure of N2O, and then decide which gases or which structures has stronger intermolecular interactions. So for example, for the CO2, the Lewis structure of carbon dioxide is this one, C, and then we have double bond over here, also double bond here, and then there are some pairs of non-bonding electrons. And then the other one is N2O. And then they have different formal charge over here. And then the other one. And then this is the formal charge, -2, +1, and +1. Okay, so among these three structures, the most stable is the one in which the formal charge is less or equal than +1 or -1. So for example, this one over here having -2, that is not favorable. So we are going to look at the first and the second structure, and then remember that the more electronegative atom is more stable if its formal charge is also negative. So for example, between N and O, the electronegativity of oxygen is higher compared to the nitrogen. So this one over here, for example, is more favorable because the oxygen has -1 and then the nitrogen is +1 compared to the second structure in which the -1 belongs to the nitrogen. So we see that based on the Lewis structure, we know that N2O is a polar molecule. So this is polar, while the CO2 is nonpolar. Now, if it is a nonpolar, the CO is a polar bond, but then because of the structure, because it is linear, then the overall CO2 is non-polar because there is no net dipole moment. But for the N2O, this is polar. So in that case, for the CO2, they have London dispersion, while for N2O, which is polar, of course, they also have London dispersion. Every molecule has London dispersion, but as for the polar molecule, it has an additional intermolecular interaction, which is a dipole-dipole. Now, this dipole-dipole is stronger compared to London dispersion. So, if we compare the CO2 and N2O, then we can say that the intermolecular interaction between N2O, which is a polar molecule, is stronger compared to the CO2. So when we condense the N2O gas, then the tendency of this gas to form liquid, meaning it forms a bonding between one N2O and other N2O molecules, then it is more favorable because it forms a more or a stronger intermolecular interaction. So in that case, the one which will condense first should be N2O. Now for the next question, here we have CO2 gas and the amount is 2.5 gram over here, and then it's introduced into a chamber with constant volume of 2 liter. This one, and then the temperature is 27 centigrade, and in this condition CO2 gas deviates from the ideality with pressure and volume correction constants A and B with each value. So the question A, calculate the pressure of CO2 gas in the chamber. Assume that CO2 gas behaves as an ideal gas. So for the question A, we are going to use the ideal gas law. So we can use the formula of PV equals to nRT. And then from the data, we know that the mass of the CO2 is 2.5 gram. And then we have volume, which is constant, 2 liter. Then we also have temperature, 27 degrees Celsius, which equals to 300 Kelvin. And then the value of A, which is the correction constant for pressure. So here we have the A value. And then we also have B, which is the correction constant for volume. For the ideal gas, we can directly calculate using the ideal gas formula. So in that case, so the pressure can be, so the P ideal can be calculated by nRT divided by volume. So we can calculate. Now the mole, we can calculate it from mass and molar mass. And then the molar mass of CO2, we can calculate this here, over here. We have carbon, which is 12. And then we have oxygen, which is 16 gram per mole. So here we have 44 gram per mole as the molar mass of CO2. Now for the calculation of mole, so we have 2.5 gram divided by the molar mass, which is 44 gram per mole, and then the gas constant, which we are going to use 0.082, and then the temperature in Kelvin. So we have 300 Kelvin, and then divided by the volume in liter, which is 2 liter. The ideal pressure 0.699 atmosphere. So the next one is we are going to calculate the pressure of CO2 gas using the van der Waals equation. So if we compare the ideal gas law PV equals nRT, then for the van der Waals equation we have pressure, but it is corrected. This is for the P, and then the next one is the volume, which is also corrected, and the other one is the same, so nRT. Now if we rearrange this formula, then we will have P and then nRT divided by the volume minus NB. So we have here, so nRT divided by the volume minus NB, and then we are going to reduce this pressure with the correction constant A multiplied by N square divided by the V square. So from this equation we know that we expect the real pressure will be less compared to the ideal pressure, and that makes sense because remember that for the ideal gas the pressure is due to the collision between the gas molecules and the wall of the container. Now if it is a real gas, then there is an interaction between the gas molecules, so that molecule A, for example, interacts with molecule B. So now the overall collision between the gas molecules in the container becomes less. So we expect to have a smaller value of pressure. So in this case here, we can calculate it. The value of the P real, so as a real gas, this is slightly less compared to the ideal pressure, and the calculation result is 0.697 atmosphere. Okay, the next question. In this condition, hydrogen fluoride HF and ethane C2H6 are in gas state. Order the following gases CO2, HF, and C2H6 based on the value of pressure correction constant A from the smallest to the largest. Now remember that the constant A, which corrects the pressure of a real gas, this A correlates to the intermolecular forces. So basically, for gas molecules which has a stronger intermolecular forces will tend to have a bigger value of A. So for example, if we see CO2 which is non-polar, and then HF which is polar, and then C2H6 is also non-polar. So for the HF, which is polar molecule, then we would expect this to have a bigger value of A because of the stronger intermolecular forces. So it is possible to have, for example, a dipole-dipole interaction. And then for the non-polar molecule, which is CO2, so this is the structure of CO2. This is non-polar. And the other one is C2H6. So we have 2 carbon and then each has 3 hydrogen. This is also non-polar. Now, if we compare these two molecules, because these two are non-polar, so they have London dispersion as their intermolecular forces. And we know that London dispersion is a weak intermolecular forces. And we are going to compare these two. Now, you see, or from the structure, that over here, so you can see from the structure of C2H6, then it is relatively has a larger surface area compared to the CO2. So in that case, it will have a stronger London dispersion compared to the CO2. So in that case, the value of A from the smallest to the largest is the non-polar will have a smaller A, and between CO2 and C2H6, the A of CO2 should be less compared to the A of the C2H6, and then these two molecules are non-polar, and this should have a smaller A compared to the polar molecule, which is HF. Now for the next question, order the following gases based on the value of volume correction constant, B from the smallest to the largest. So of course, the B constant relates to the size. So if we have, for example, a more compact molecule, then it tends to have a smaller value of B compared to, for example, a larger molecule. So if we compare between CO2 and C2H6, we know that from the structure, C2H6 is tend to have more contact area. So the probability is that the size of C2H6 will be bigger compared to the CO2. So in that case, we can predict that the B of the CO2 should be less compared to the B of C2H6. Now, the HF, if we see from the standpoint of molecule, it is actually has a smaller molar mass. But then, if we see this based on the intermolecular forces, we know that HF has a strong intermolecular forces compared to the other two molecules, so it tends to interact with other molecules more. So in that case, the probability of this HF to take some volume is actually larger compared to the other. So the B of the HF should be the largest compared to the other two molecules.